Hello, this is Mrs. Sargent, and this is 12.3, determining the form of the rate law. So, when you're determining differential rate laws from experimental data, if you are doubling the initial concentration of the reactant, this causes the initial rate to double. So, since it's doubling and doubling, that's 1 for 1. So that's a first order. If you're doubling the initial concentration of the reactant causes the initial rate to quadruple, that is second order. So how I kind of like to think about this is, so the concentration is doubling, so that's 2 times, and then the initial rate is doubling, so that's also 2 times. So 2x is equal to 2x. This is just 1 for 1, so that's first order. Where here, our concentration is doubling, so that's 2x. And then our initial rate is quadrupling. Quadruple would be 4x. So 2 is not equal to 4. So 2 squared equals 4. So that 2 there tells me it's second order. If you're doubling the initial concentration of the reactant causes the initial rate to increase 8 times, then that is third order. So 2 to the third gives us 8. So that third here is the third order. If doubling the initial concentration of the reactant doesn't change the initial rate, then you have 0 order in the reactant, and that reactant is removed then from the rate law. So I know this is a lot of words, so now we're going to look at this in action with some examples. So our first reaction, we have 2A reacts with B, and this forms 2C. So what I want you to think about is a look where the, we're just going to look at A to start with. So here, like this is trial 1, trial 2, trial 3. So I'm just going to label trials over here. I'm going to try to. So from trial 1 to trial 2, we have a constant concentration here. So we don't see any change in the concentration of reactant A. When we look at the concentration of B, though, this is doubling. So it's 2 times. And the rate here, where the concentration of B is doubling, the rate is also doubling. So this is where 2 is equal to 2. This is going to be first order for B. So remember that we talked about in our last video that rate is equal to K times the concentration of one reactant times the concentration of the second reactant. And so right now we know that B is first order. Okay? So now we're going to look at trial 2 and trial 3. I'm going to just change colors here. So here we see that reactant A is doubling, okay? And reactant B is constant here. So when reactant A is doubling, the rate is quadrupling. So in order to is not equal to 4, but 2 squared is equal to 4. So the order for A is second order. So the reaction is second order in terms of A, and it is first order in terms of B. So the rate law is going to be rate equals K times the concentration of A squared times the concentration of B. So then in order to find the reaction order overall, we just need to add the exponents together. 2 plus 1 gives us a third order overall. So here in this second example using actual chemicals, we just start looking here, and this is constant between the first and second trial for the ammonium ion, and then 0.0050 going to 0.010. So this is doubling. NO2 minus is doubling. And when we look here at the rate, we need to figure out what's happening. Now we can see that they have, it's 1.35 times 10 to the negative 7th and 2.70 times 10 to the negative 7th. So they're both to the same power. When we look here, 1.35 to 2.70, that is going to be 2 times as well. So the rate is going to be equal to K times the concentration of NH4 plus times the concentration of NO2 minus. And so with 2 times to 2 times, that's 1 for 1, so that is first order. And then for our other reactant, if we look at, this is doubling here. This is being held constant. And then here to here, this is also doubling. So this is also first order. So the reaction is first order in terms of the ammonium ion, and the reaction is also first order in terms of the NO2 minus ion. So the rate law is equal to K times the concentration of the ammonium ion times the concentration of the NO2 minus ion. And the reaction order overall, 1 plus 1, gives us second order. So here is another reaction. One thing that is different about this reaction is we only have one reactant. We don't have 2 reactants in this. So we can really pick wherever we want to. Look at this. I'm just going to start here with first trial to second trial. If it's easier for you to go in second trial to third trial, that's fine. But this is doubling here. And here, pay attention to the exponents are changing here. So this is 0.0003, and this is 0.0012. So this is 4 times here. So the 2x is not equal to 4x, so 2 squared is equal to 4, so this is second order. So the rate is K times the concentration of A squared, and because we only have one reactant, overall this reaction is also going to be second order. So with the first 2 examples that I showed you, we were holding something constant throughout. You do not have to hold anything constant. So below this example, you don't have to hold anything constant. And then we have another example to take a look at here. A plus B produces C. So here, this is doubling. This is being held constant. And the rate is being held constant here as well. So what this means, the concentration of A is changing, but it has no effect on the rate law. Where then here, with B, this is doubling, and it is also doubling the rate. So this is going to be first order in respect to B. So rate equals K times the concentration of A to the 0 power, B to the Y power, and that Y power is 1. So because A has no effect on the rate law, so because of that, we can remove it from the rate law equation. So here's an example. See, I would like you to try to determine what the rate law is on your own. We've looked at a few examples now. I want to give you guys a chance to try one. Let's go ahead and pause the video. Welcome back. Here we have our overall reaction. It was studied that at -10 degrees Celsius was obtained. We have this rate is equal to the concentration of chlorine over the time. So we have constant rate of NO, and chlorine is doubling. And the initial rate is also doubling here. Then when we look at our other reactant, here it is doubling, and here is being held constant. And this 0.36 to 1.45, that is quadrupling. So for your rate law, you should have written rate equals K times the concentration of NO, 2x to 4x, that is going to give us second order, times the concentration of chlorine, and that is to the first order. So part B is asking, what is the value of the rate constant? What is the value of our K? So we can choose any line in our data to solve for K. So I'm just going to pick this first line. The initial rate is 0.18. That is equal to K times the concentration of NO is 0.10 squared times the concentration of Cl2, which is also 0.10, that's to the first power. And when you solve this, you should find that K is equal to 180 liters squared over moles squared